Section 12.6 deals with two types of surfaces that we're going to see in 3 space. Remember, a surface is a two-dimensional shape. It would have surface area, but not volume, but it's going to be living in 3 space. The first type of surface is a cylinder. That's also sometimes called a cylindrical surface. Okay. And the second type is quadric surfaces. In this first video, we're going to be taking a look at cylinders, and I'm going to start with an example. If I look at x squared plus y squared equals 1, and I want to graph that in 3 space. So you'll notice it's an equation that only involves 2 variables, but I'm going to be graphing it in 3 space. Now, because the 2 variables are x and y, I had to tell you we were in 3 space. If the variables had been x and z, it would be clear that we were in 3 space because there's no z value in the xy plane. Okay. All right. Now, usually if I'm graphing something that just involves 2 variables, I will start with a picture in the coordinate plane. In this case, it would be the xy plane because x and y are the 2 variables in this equation. And I know in that plane, we would just have a unit circle. Okay. All right, so now in 3 space, I would want to draw that same unit circle in the xy plane. And it might not look perfectly round. There are a couple of reasons for that. One is I drew it, and I'm not perfect, and I sometimes draw circles that aren't perfectly round. But this one actually isn't supposed to look perfectly round because things are warped a little bit when we're trying to draw 3 space on a 2-dimensional whiteboard. Okay, now I haven't drawn the surface yet because this is still just a curve. That's just the circle. Okay. The equation does not put any restrictions on z. When I drew in the xy plane, I was holding z to be 0. Z is free to be whatever we want. So I'm going to get a copy of this circle at every single height. So in every plane parallel to the xy plane, we're going to see this same basic circle. So to show that, I'm going to extrude, in this case, parallel to the z-axis. So whichever variable doesn't occur in the equation, I translate the curve. The fancy word for that is we're going to extrude the curve parallel in that direction. So what I'm going to do here, this point right here is actually the rightmost point on the graph. And this point is actually the leftmost point. But it doesn't look that way the way I've graphed this. I'm going to pick what looks like the points that are farthest to the left and farthest to the right. And I'm going to extrude those. So I'm going to translate parallel to the z-axis, and I've sort of picked a distance, and I came that distance up and down. I'm going to do the same thing over here. Go that distance up, extrude that distance down, and now I can connect these points with a copy of that cross-sectional curve. And so what we're getting is literally a cylinder. If you extrude a circle, you will get something that you're used to calling a cylinder. Okay. Definition of a cylinder is just that you take a curve that lies in a plane and you translate it parallel to some line. We're in particular going to be translating or extruding parallel to one of the axes. So we're just looking at cylindrical surfaces where the extrusion is done parallel to one of the coordinate axes. Here's my eraser. And so we're going to be looking at graphs of equations in 2 variables, but where the graph is in 3 space. So let's try another one. We call these things cylinders or cylindrical surfaces, even if we're not extruding a circle. If I try to sketch y equals e to the z, that's going to be a cylinder under this new definition of cylinder, that it's just an extruded plane curve. Okay. So I would start, since y and z are the variables that show up here, I would start by just graphing this curve in the yz plane. Now, I do need to be careful here. In the yz plane, z is the vertical axis. In the xz or the yz plane, that's the standard orientation. In the xy plane, y is the vertical axis. But in the YZ plane, y is horizontal. Okay. Now, I'm used to having equations solved for the variable that's on the vertical axis. This is solved for y, which feels familiar at first until you realize that that's on the horizontal axis. So I've got a couple of options. One is I could solve this for z, and I could say z is the natural log of y, and then I could sketch that curve like so. The other is I could say I want to work with the exponential function. I'm used to having y equals e to the x. So y is in the output position. That's the same thing here. Notice y is always positive. So here y has to be always positive. Now instead of just having the graph on the top of the page, that means we have the graph on the right side of the page. Here, where x is the exponent, the negative x-axis is an asymptote. Z is the exponent, the negative z-axis is the asymptote. So I do just need to be careful, even when I'm working with familiar-looking functions, that I pay attention to what variable's in what position. So now, if I want to sketch this in 3 space, I'm going to start by drawing in my axes, and I don't think I want that to be quite so shallow. I'm going to start by drawing in my axes, and then I'll draw in that curve. And I'm going to draw a second copy of that here. I'll try and keep these looking pretty similar. Okay, that looks pretty similar. Just because there's a neat trick that I want to show you, but that might not occur to you at first. So I'm going to not use the trick here, show you what goes wrong, and then use the trick here. All right. So what I want to do is I want to now extrude this parallel to the x-axis. So I want to choose some important points. Pretty clearly the starting and the ending points should be important. And I want to extrude forward and back, making sure that I'm parallel to that x-axis. And I tried to keep the same distance that I extruded forward and back. And now I'm going to do that with this point up here as well. So I'm going to extrude forward, sorry, this is backwards, and then forwards that same amount, making sure that I'm parallel to that x-axis. Okay. And then I want to connect the points. Notice that the original curve is connecting the midpoints of these line segments that I've created. This point and this point are the frontmost points. I'm going to draw in a translated copy of the curve to connect those. This point here and this point here are the backmost points. I'm going to draw in a translated copy of the curve, curve to connect those. Now you'll notice when I do that, it looks kind of weird because these curves cross each other and I have this sort of weird little bobbly bump in my shape here. Now that shouldn't actually be happening because if I've got a curve like so and I extrude it, it's nice and smooth all along here. One thing that's happening though, you'll notice I've got pink and yellow here. If you look at this head on, sometimes you're seeing pink, sometimes you're seeing yellow. We're sometimes seeing different sides of this surface. So I can clean this up a little bit. If I know this is going to be nice and smooth, rather than having these bobbles here, I could connect that to make that smooth. And then I might try to use some shading to sort of show that some of the time, like up here, maybe I'm seeing one side of the surface, and then what I didn't shade in red is the other side. So almost like what I've done is just shaded the pink where you're seeing the pink, and what I didn't shade is the yellow. Okay. Now, what can help with that, to avoid getting that weird little bobbly bump that we had, here I've just extruded what were obviously important points, my starting and my ending point. I'm going to also extrude this point right here. Now, from the initial picture, it's not at all obvious that that's an important point. But if I take a look, once I've extruded here, it looks like that point is the farthest away from this line, which is parallel to the x-axis. And if I extrude that, and then I connect the dots with these front points to front points and back points to back points, notice by extruding that, that's almost like what I had here when I cleaned up that little weird bobbly shape that I had from it, the curves crossing. That's how I sort of connected that. So sometimes there might be a point that's important to extrude, but that's not super obvious from looking at the shape of the graph until you've extruded your starting and your ending points. Okay. Now, is either of these a beautiful drawing of this? No. Okay. In general, when I'm drawing these things, there's a lot of erasing and redrawing, and it's even harder to do on a whiteboard than it is on a chalkboard than it is on a piece of paper. So there's usually a lot of erasing and sort of cleaning things up. What I will be looking for, I do expect you to be able to draw these things. I don't expect them to be beautiful, but I expect to be able to see the curve. I expect to be able to see that you have extruded parallel to the missing axis. That's key. Gotta be parallel. And then if you get something that looks just like a bunch of weird curves, I do expect you to clean it up a little bit by straightening out some things and maybe using shading to clean things up. But I don't expect your curves to be utterly beautiful. I expect them to suggest the shape that you're trying to get.